we're going to jump back into where we were on Friday, dealing with these pre-existing stereo centers. So we talked about that, like how pre-existing stereo centers, how they affect the stereochemistry of a reaction, right? We use this example, said that this stereo center right here would block one face and make the other face more accessible. And we said that since it was wedged, which is coming out of the screen, then that same face would be blocked. And the other face, which would be coming from the opposite side of that, will be open or more open. So these are the two products that resulted from that, two epoxides, and the one where the stereochemistry of the epoxide is wedged, as well as the substituent. We call that the minor product. And we said that the one where the epoxide was dashed or going away from that stereo center was the major product. And that all happens in the transition state, which we talked about, the approach of the oxygen and how it comes in and attacks the alkene, so on and so forth. So let's look at another example of that. And we're going to look at two examples. And then we're going to start a little bromination today. I'll just introduce it to you in the time that's left. All right. So first question says hydroboration. If you remember that reaction, hydroboration oxidation, it's a way to convert alkenes into alcohols. So it's like it's one of our methods for converting alkenes into alcohols. All right, so it says hydroboration, oxidation of R-trimethyl, 2-methyl undeck, 2-ene, 4-bloxysilane, don't worry about all that, yields two stereoisomeric products in different amounts. So that the two stereoisomeric products in different amounts, what do we call that? What's the terminology we use for that on Friday? That ratio of products. Say it again.
Non-racemic.
Okay, yes, it is a non-racemic mixture. It's an unequal mixture of isomers. But we had another name or another term that we used, and it was the product distribution. Right, that's just a fancy term for the ratio. So it's 80 to 20. That's the ratio. And it asks, first question asks, which product would you expect to be formed in the highest amount? It's kind of a giveaway if you look at the ratio that's down here, but let's go to the next question, because we can see that it's this product that is the major product. Remember, the major is formed in the highest amount, and then this product is minor. All right. Now the next question asks about the relationship between the two products. What is the stereochemical relationship between A and B? Are they enantiomers? Are they diastereomers? What are they?
Diastereomers.
Diastereomers.
They're diastereomers. Very good. And you know that because of what?
The switch is,
The OH is facing.
yeah, it's dashed.
So the OH is different in each product, but this stereo center is fixed. Is that right?
Yes.
Yeah. So you only switch, the difference is in one stereo center and not both. If it was both, then they would be enantiomers. All right. Let's look at C. C says explain why the products are formed as an unequal mixture. We already see that they're unequal. It's an unequal mixture based on the ratio, 80 to 20. So you got more of A than you have of B. The question is here, why they formed as an unequal mixture? Anybody? All right, and again, think about the topic that we're discussing. We're talking about reactions on molecules that have pre-existing stereocenters. And so the crux of that argument up front is that the pre-existing stereocenter is going to create a bias. It's going to make one product be favored over the other. All right. So to answer C, explain why the products are formed as an unequal mixture. We're going to dig that out a little more, but can somebody explain that in your own words?
Because in the A, the OH is facing opposite way of the pre-existing stereo center.
Okay.
And B is facing the same way, so it kind of blocks it.
Okay, great. So what does that mean in terms of the ratio? Why do you think, and I don't think we talked enough about this on Friday, but why do you think being away from the stereo center is good? What's the terminology? We learned it in part 1.
Was it the transition state?
Okay, yeah, it is. It does have something to do with the transition state.
Like the energy lower?
Yes.
But with the lower energy?
Yeah, so one of them is going to be formed through a lower energy pathway, right? And it's going to be the one that where there's the least amount of steric interference between the two substituents. I don't think we talked enough about sterics, but let me give you some. I know it was in the video though. Right, so this pre-existing stereo center is going to cause what we call steric hindrance. Right, so it's going to force anything that's trying to react on that double bond to have to work around it. So it's either going to try to come in from the same direction or it's going to come from the opposite direction. But either way, it's going to follow the lowest energy pathway. Right, so if we had let me put the date up here too. Before I forget. Right, we have a energy diagram, like that intermediate is right there in the middle. So that's the starting material. And then we have one pathway where we get here. We have another pathway to get here. Let me make that reflective of the fact that one of those products is a little higher in energy. Right, so you can see right here, this is my starting material. This is the transition state for one pathway. This is the transition state for the other. Hold up 1 second. That's my transition state for the other. So this is, which one of those reactions do you think is going to be faster?
The second one?
The one on the right.
Yeah.
The,
the smaller one.
This one.
Mm-hmm.
Okay. Why do you say that? You're right. You're 100% correct.
Because it's smaller, so the
Activation energy.
Yep, the activation energy is smaller.
Right here. Good. Very good. So that would be delta G double dagger. And then over here, you look at this activation energy. It's way higher. And that is what controls the rate of a reaction, right? The activation energy. So when you look at the two products, one of those is going to have a much lower activation energy than the other, right? Let me put that up here. Right, so a higher activation energy is going to slow the rate of that pathway. So this pathway on this side would be the same side. I'm just going to say same side pathway. Where the reactant would try to come in from the same side of as the pre-existing stereo center. And then over here would be the opposite side pathway. Right, so lower activation energy. So that's the like the concept behind this. So the reason why they're formed as an unequal mixture is you basically have a competition between two pathways, right? And the lower energy pathway is going to predominate. And the lower energy pathway is going to be the pathway that produces stereoisomer A, where there's minimal steric hindrance between the OH group that's added in and the pre-existing stereocenter. So I'm gonna write that down. Right? Well, any questions about that? So when we talk about sterics, just think, I know it's a weird term, but just think about in terms of touching. Like those groups, those atoms do not want to touch each other, right? So they want to be away from each other as far away as possible, especially if it's something bulky like that silane that's on oxygen on the pre-existing stereocenter. So you don't want those atoms to interact with one another, to see each other. So they want to be as far away as possible. So that's why you get that unequal mixture of stereoisomers. All right, questions about that example? All right, let's go to the next example. And does anybody remember this reaction before we start? Because this is going to take some time if we don't know what this is. Anybody? What oxymercuration is? If you took me for part one and you don't know this, you need to drop. I'm joking. Don't drop. Anybody? Well, you can hear a rat peeing on cotton. It's the quietest that it's ever been since August or whatever, whenever we start. Whenever we start. All right. Let me throw in a page. I'll put it here. All right, so this is oxymercuration. If I can spell it. Come on, Russell. Right? And that's another reaction that converts alkenes into alcohols. So if I have an alkene like this, and I treat it with mercury acetate in the water, and then follow that up with sodium borohydride. This is a reaction that we learned in part one when we were talking about alkenes. All right, and this is different. It's in the same class of reactions as hydroboration, but the regiochemistry is different, right? So let me just show you right quick what I'm talking about. I don't want to be just banging my head against the wall. So this is right. So that is the hydroboration. The reagents for hydroboration, and then the reagents for oxymercuration. Right. So with hydroboration, it converts the alkene to an alcohol, but it is what we call, this might refresh your memory, is anti-Markovnikov. Right. What that means is that the OH adds to the least substituted carbon in the alkene. All right, let me pick a different highlighter than that. And then for oxymercuration, it's the opposite. There's more carbonyl addition. So this is, your OH is going to end up here. On the most substituted carbon. So this is more carbonyl addition. Let me find some room to put that. I'll put it here. Right. So OH ends up on the most substituted carbon in this case. And then with the hydroboration, which we just saw top two, it ends up on the least substituted carbon. And to illustrate that, let's go back to that example. I'll go back to that in a second. But if you look at the alkene here, you can see that one of the carbons is more substituted than the other. So this side is the most substituted, and then this side over here is least substituted. Right? All that means is that it has less groups attached to it. Right? So down here, right, these two reactions, they're in the same class. They're both ways to convert alkenes into alcohols. The difference is the regiochemistry. One, the OH adds to the least substituted side, and one, the OH adds to the most substituted side. All right, so, and we call that either Markovnikov, which is to add to the most substituted, and then anti-Markovnikov. I think when I taught this in part one, I gave y'all like a mnemonic to remember, like BAM and MEM. Boron is anti-Markovnikov. Mercury is Markovnikov, but y'all probably forgot it. All right, let's go back up here to this reaction. So I got the, I'm running this reaction under oxymercuration conditions, and it says the same compound produces products in relatively a 50-50 ratio. So did that ratio go down or did it go up compared to the top reaction?
It went down.
It went down, it went way down, right? So there has to be a reason for that, right? And so when you think about the pre-existing stereocenters, what do you think about? What are the two factors that kind of dictate the outcome of the reaction, the stereochemistry of the reaction? What two factors about related to that pre-existing stereocenter? Anybody remember?
Size and
Size is one, good. What's the other one?
Proximity.
Proximity, good. And when we say proximity, what is that in reference to?
How close it is to the reaction site.
Yes, the proximity to the reactive site, how close it is. The closer it is, the more influence it's going to have. The further away it is, the less influence it's going to have, right? And size is just a steric bulk, right? The size of that group, as it gets bigger, is going to have more influence. If it's smaller, it's going to have less influence over the stereochemical outcome. All right. So without holding you hostage, trying to force you to remember this reaction, which carbon in that double bond is going to become an alcohol under these conditions?
Could you repeat that again? You kind of went in and out.
The last question, the question I asked?
Yeah.
Yeah, so I'm asking which carbon in that alkene is going to become an alcohol?
the one at the top.
This one?
Yeah, the one with the double bond, because it's an alkene, right? And it's
Yeah,
converted
so-
from an alkene to alcohol.
Right. So let me rephrase the question. This is my alkene. In that alkene, I have a carbon on this side and a carbon on that side. Is that right?
It's the one on the
Yeah.
right.
The one on the right?
Yes, sir.
Yes, because it is what? More substituted. Just like we just showed in the example down below, Let me go back to that real quick. We said that for oxymercuration, the most substituted carbon in the alkene is where your alcohol ends up. And that's without going through the mechanism and all the details behind that, right? But just for the sake of time, if you have an alkene and one side is more substituted or has more substituents or groups attached to it than the other, then that is the carbon under oxymercuration conditions that's going to get converted into alcohol. All right, so let's go back up to here. We can see obviously that we have two carbons and one of them has more groups attached. Am I right? Can you see that? The carbon on the right has a methyl group and an ethyl group attached to it.
Yes.
So that's my most substituted site. So in my product, let me see how many carbons. Let me make sure. I want to make sure I draw that chain with the right amount of carbons. All right. So in the product, this is going to be, let me put my substituents in. The OH is going to be here. Right? Is that right? Because that is the more substituted carbon in that double bond. Remember, this is the double bond, and those are the two carbons that react. Yes, no,
Yes.
Yes.
right? And I'm just going to cheat and copy this. All right. The only difference in this other product is going to be the stereochemistry of that OH bond. That's going to be on a wedge. Are y'all following that? I'm going to get those two isomers though, right? Am I right?
Yeah.
All right. So now we've drawn the products. I spared you. Normally, if we were in class, I would have you doing this in groups, but I spared you the agony of doing it. All right. So we drew the products. Let's do part B. Explain why there's a decrease in the ratio. All right. Somebody help me out. I'm gonna put lunch on the line, by the way, for this. $20.
Something to do with the wedge and the dash line of the OH.
Well, you're gonna get both of those products just based on the fact that you have a chiral center present, right? But I want you to think past that. Think past that part and think about what we talked about initially. What two factors determine the stereochemical outcome if you have a pre-existing chiral center?
Is it because it like moved away from each other a little bit?
Who was that?
Juanetta.
Okay, yeah, put your cash out in the chat. Yes, that's exactly right. It moved one carbon. All right, are y'all following that? Look up top. Look where the OH is up top. Do you see where it is in relation to the chiral center? It's right
Yeah.
next.
Yes.
It's adjacent to it. Am I right?
Yeah.
And if you look at it here, it's not. It's one carbon away. And those subtle details change reactions drastically. It might seem like it's subtle to us, but we're talking about working on an atomic level, right? So those small perturbations make a big difference. So the fact that it's further away from the pre-existing chiral center means that the chiral center is going to have less influence over the outcome, right? Are y'all following that?
Yes.
So it's added. Further away from the chiral center, right? So that's gonna cause a decrease in the selectivity, right? And it's gonna cause a decrease in that ratio. Now, I made it drastic like that to make the point. It may not necessarily be 50-50, but it's definitely going to decrease because that stereo center that's being formed is further away. So the pre-existing chiral center has less influence because of that. So we'll put that here. Right, it's going to have less influence due to its proximity to where the reaction is taking place. All right. Any questions about that? All right. Let's answer number 3. I'm gonna be quiet for a second and let you answer that. So the reaction, when the reaction is carried out with this alkene, would you expect the ratio of stereoisomers to change, or would you expect a major product to be increased? So if you notice on this alkene, the substituent is now this. So it's a silicon with 3 terpbutyl groups attached to it. All right. So what do you think? If I put terpbutyl groups on that silicon instead of methyl groups, what do you think is going to happen? Or if it is anything going to happen?
That increases the size, right?
The bulk, the size goes way up, right? So do you expect that to have an effect on the ratio?
Yes, sir.
Yes.
Yes.
We don't know what extent, right? We can't prove it unless we actually did the reaction. But it's going to affect the ratio of stereoisomers just because you made the substituent bigger. Even if it's a little bit further away, if you bulk it up, it's going to increase the amount of influence that it has on that on the reactive site. So would you expect the ratio of isomers to change? Yes. Right, so when you bulk up that substituent, of course, it's going to have an impact. We don't know the extent of it, but it's definitely going to change the ratio. Right, that substituent on that pre-existing center, if it's bigger, it's going to have some effect. All right. And then would you expect the major product to be increased? What do you think?
Yes.
Yeah, of course. It's going to, if you bulk up the substituent, that's going to make that the face that it's facing less accessible, right? And this is facing, this is on a dash, so it's going to be blocking the back face. So it's going to make this product more prevalent. Is that right? Where the OH is coming from the opposite side. Do you agree with that or no?
Yes.
Yes.
All right, so that product that's circle, or not circle, but highlighted in yellow, that product is going to become major if we bulk up that substituent. All right. Any questions about the pre-existing stereo center concept? Right. What do we know? Like let's recap that. Let's recap it. I'm gonna put a page in. actually. Let's add it underneath it. I'll rearrange this before I post it to Blackboard too. So let's recap that just to go over like the major points. Okay, so the first thing we said was that if you have a molecule with a pre-existing stereocenter, it's a way to generate a non-racemic mixture. So you'll have an unequal mixture of stereoisomers. Anybody remember what the formula was? Not really a formula, but like how we can, another way we can say that. Chiral plus what?
Chiral plus achiral.
Yes, good. Right, so you take something chiral plus something achiral, you're going to get a non-racemic mixture. What else can we say about it? We can say that the size of the substituent on the chiral center will dictate the outcome. Is that right?
Yeah.
Right. What else?
Proximity.
The proximity of it is going to also, I'm going to cheat again. Don't hate me for that. So the proximity, let me make that more detailed, because it's the proximity of the substituent to the reactive site. Right, that also dictates the outcome. Further away it is, the less influence it has. The closer it is, the more influence it has. All right. What else? Am I missing anything? I am. What do we know about the path, the energy? What can we say about the energy?
Like the lower activation energy was most likely the opposite side.
Okay, I like that. So we're gonna say the lowest energy pathway is the one with the least steric what?
Hindrance.
Steric hindrance. All right, so those four things that are the main takeaways from this idea about these pre-existing chiral centers. that size, proximity matters. A pre-existing chiral center in a molecule is going to guarantee an unequal mixture of products because it's chiral. And then when you add something achiral to it, you're going to get a unequal mixture of stereoisomers. And then the lowest energy pathway is going to be the one that incurs the least steric hindrance, right? So that's normally going to give, I heard you, T, he said that is going to give you the opposite product more than likely of what the stereo center is. And that's correct 95% of the time. Sometimes you'll have a special case where you might have another factor that affects the transition state that might overrule sterics, right? But sterics, if sterics are your major determining factor, then the lowest energy pathway is always going to be the one that avoids that steric hindrance. All right, any other questions? Any questions about anything up to this point? Hold up. All right, so I sent a video on Friday. So what I want to do now, because this is the last concept for stereochemistry that we're going to cover, what I want to do now is introduce you to the next topic. And then that way Wednesday, because I think we're going to run out of time, but Wednesday we'll hit it, starting with a Lilly bromination. And then we're also going to talk about conversion of alcohols into alkyl halides. So between Wednesday and Friday. So let me introduce that. If I can get my tablet to do right. Here. And this is under the larger topic of the synthesis of alkyl halides, because we're going to take this alkyl halide concept and we're going to talk about how to make them and then how to use them, because there are a lot of different applications for them. Right, so the first method that we're going to talk about is a Lilly bromination. And before we go any further, everybody is familiar with what an alkyl halide is. Am I right or am I wrong? Or do I need to refresh you?
Could you give us a refresher?
No, I'm joking. Yeah, so alkyl halide is just a functional group that contains an alkyl group as well as a halogen.
Thank you.
No problem. Hope you didn't take my joke the wrong way. I joke a lot. All right, so you got an alkyl group and you have a halogen somewhere attached to that group. So that's what we call an alkyl halide. All right. So Lilly bromination is one way to make these. It's a derivative of an alkyl halide. All right. So we have a alkene, and we have let's just say a methyl group here, a terminal, a Lilly bromination. Right. You use MBS and light, and we're going to discuss this in detail. So don't worry about all the dirty nuts and bolts of it just yet. But that's going to give you a product that looks like this. Where now the CH3 becomes a CH2, so one of the hydrogens gets removed, and I add a bromine on the end. And we're going to talk about the mechanism and all that stuff. And then another set of reactions is, I'm going to say 2A, B, and C will be conversion of alcohols. Right, so you can take a primary alcohol, and you can use a couple of methods. You can use PBr3, or you can use thionyl chloride. Let me move that because that's cool. Right? And that's going to convert, this will convert it into a bromide, and then this will convert that into a chloride. So we're going to talk about how these work. I have a handout for it. I just didn't alert you to find it. And I knew we wouldn't have time to finish this because I knew we had to finish the other topic. All right, so that's one way. And then there's another way with alcohols where you have a OH, and notice this is a primary alcohol. This is a tertiary alcohol. And then you just treat that with, let's say, HBr, and you end up with a bromine in the place of alcohol. All of these are substitution reactions. All right, we're going to stop here. It's 9:52, and then we'll pick this up on Wednesday. If you would, let me show you where that handout is real quick. It's in assignments, and it's under right here in class hand. And if you're looking for this, the stereochemistry handout is right here. The Lily bromination is right here. So if you click on that handout, and this is what we'll be working from for this section. All right. Any questions about anything?